My name is Ray. I'm from Uber. I want to begin my talk by sharing a story about me with Uber. That was about 7 years ago, a rainy night. I was a graduate student. My car is broken. I want to get a car. Okay, about it. I think people know what Uber is doing. All right. So today I'm going to share some exciting research and engineering applications about Uber AI, and I hope you found it interesting. But before we dive into the topic, I just want to briefly talk about machine learning and AI at Uber. First, why the machine learning and AI at Uber are kind of special. Here you see like trip kind of forecasting about San Francisco at the headcount level over a period of time. I believe it's 1 day. So yes, Uber operates at spatial and temporal and the physical world. So we operate at we have been maintain a very complicated network with human involved, and also there are tons of economics going on, which is a very complicated model. And finally, our daily job is about moving people and things, real people and real things. So of course, as you can imagine, the efficiency issue, safety issue, and the security issue are like very important for our daily work. So there are tons of applications of machine learning at Uber. Basically, you can say machine learning is fundamental to Uber's business. I can only list a few here, but list can go on and on. So for example, we need to model the marketplace dynamics, like the ETAs, right? How long to a car to reach you. We will model the traffic, the events, and of course, what's going on in the city. Also, we are trying to use these models to predict supply versus demand, or how many cars on our network, how many riders are going to take, right? And also, of course, this is a money system. So we have to determine a price and optimize that price and our incentives to make sure the market works well. We need to do routing, dispatching, and there are all kinds of other applications, including safety, fault detection, autonomous driving, and as we are expanding into more areas, the other than ride sharing, for example, Uber Eats, food delivery, and Uber Freights, the truck system, right? We need to talk about recommendation, which we're talking about how to use machine learning to do bidding in this double-sided market for Uber Freight. So we have this organization newly formed called Uber AI, which brings the talent of research scientists and engineers into like a unified org, where we are looking to various aspects of AI technologies, which includes deep learning, reinforcement learning, Bayesian optimization, and all kinds of other important and interesting technologies. And we are not just interested in research. We're also interested in bringing research into real life, into production. While we are doing this active work in machine learning and research, we also contribute to the community. So we have a lot of open source projects. We regularly publish at top machine learning conferences. Here I just name a few of our most popular open source package. Pyro, which is a large-scale probabilistic programming language. We have Horowat, which is endorsed by many companies, including NVIDIA, to do distributed training for TensorFlow and PyTorch, and a few other platforms. And finally, we have recently released Ludwig, which is a code-free deep learning toolbox, which you will hear from us next week at Uber Palo site. So if you get a chance in, and please come, and you will see what this Ludwig can do for you. All right, so let's get to our main topic today, which is open-ended reinforcement learning. It's an ongoing research and application subject and project here at Uber AI. It's all about creating and solving diverse challenges in a single run of the program. Let me begin with talking about my view of machine learning and AI. I think people are often view machine learning and AI as a toolbox for solving given challenges, right? So in this famous image classification task of computer vision, we see that researcher has really pushed a long way to basically conquer this challenge. And we have seen that since 2010. Within less than a few years, people have basically created machine learning algorithms which can beat human, reliably beat human. Let's get to our main topic today, which is reinforcement learning, right? If you read a lot of these reinforcement learning plots, papers, and blog posts, you see that deep reinforcement learning become popular again since 2013 to 15, where DeepMind introduced this deep Q network, where all of a sudden it can place the old game called Atari games, or all the categories of games called Atari games, and just based on the pixel space. So the input to those algorithms are just the pixels. And then they're able to learn how to play and come up with a strategy for a good portion of those games. They can play really well. And there are tons of research focused on those domains. And one of the recent research actually comes from Uber AI, which we develop a way to solve this very infamous, basically, game, which is very hard to solve. It's called Montezuma's Revenge. So I will not go to details, but the challenge is, as this guy jumping up and down towards all the rooms, he actually gets no reward signal. You don't know whether it's a right move or not until it gets killed by a skull. It still gets no negative reward, right? You get killed by a skull and start again until you get that key and opens the room opens the door for the next room. You get a good big reward. This is a sparse reward problem, which has been nauseously hard to solve for many machine learning, for many RL algorithms. And of course, AlphaGo, right? When you're talking about reinforcement learning, you have to mention AlphaGo. So we have seen that AlphaGo and its variants from DeepMind has reliably beat the world's best human profession players, which makes me much less ashamed of myself. When I gave up Go when I was 10 years old, when I'm constantly beat by my cousin. So they have a movie there. They actually shoot a movie about AlphaGo called AlphaGo movie. So go ahead to watch it, but you probably have to pay. All right, so far the story is great. Like AI solving everything, right? Like, but we want to ask more, right? Like, so far AI doesn't sound very creative to me. It can solve given challenges, but can it be even more creative? In the sense that, can it invent diverse and interesting problems by themselves and solve it by themselves? Also, can they share and learn from all these diverse experiences by creating all these problems and solving them? And could they build their own curriculum and teach themselves to solving really, really challenging problems that it cannot be solved directly? So those are the questions that we ask here. So talking about creativity, looks like machine learning and AI does have some creativity in generating new media and designs. For example, GAN. You probably heard about GAN a lot. Since 2014, there has been tremendous progress in this fascinating research area. This is one of the newest research come from Google called Big GAN, right? They generated images that are very much resemble the training set. Basically, you very hard to distinguish those pictures generated by this technology from the true picture that exists in the nature. So all these pictures actually come from the GAN. So this is when your GAN did really, really good job. You got these pictures. But if your GAN did really, really, really good, what will happen? You sell it for $500,000 and you collect a little bit of fortune. Okay, but actually instead of talking about GAN, I want to take a step back to almost 10 years ago. when there's a group of very, very talented computer scientists, they put up this website, right? On the back end, they're running this, this technology called CPPN. It's basically an evolving neural network, which can paint a 2D picture with infinite resolution. And of course, it started with random images. And then users will come to this website and they will pick which one they like. And then they will vote which one are really good, starting from completely random, right? So at first it's purely random. But all these preferences goes back to the backend AI algorithms. And it starts to try to evolve itself to paint pictures that it thinks will appease this people. But people are come at different time, right? These people are preferring this. That people are preferring that picture. So over the time, they accumulated some very interesting picture. Some of them are very realistic. Some of them are kind of scientific. Some of them are also kind of like science fiction. But they looks interesting, don't they? And there seems have some creativity here. In fact, when the researcher look deeper into how this image came from, right? They can trace, starting from a random image, how these images are gradually grow from one image to a group of images to finally these final products, which seems make sense. What they found is they identify some stepping stones. Stepping stones are, in order to get this final image, what it had went through. And so they often see that. The stepping stone image are often never look like the final image. They're like very different, right? And also they found out that people are searching for something, but eventually the system gives them something else, which they found very interesting. So this open-ended process with human in the loop actually exposed some creativity. So look at this Jupiter image, right? It comes from some kind of a dark-ish thing which has nothing to do with Jupiter, but eventually grows into a Jupiter. So this open-ended reinforcement learning or open-ended AI algorithm is about bringing the best of two worlds together. We know some AI algorithms can solve some given challenges really, really well. And then we know that we could come up algorithms which can create new design and challenges. So we want to have algorithms that are combine the problem-solving capability and creativity of AI. And it could start with simple challenge, and it can solve it. And then it increase the challenginess, the challenging of the problem a little bit, and then they solve it. Along the way, they create very interesting and diverse challenges, and for each of them, they will find some solution. This is very much mimic like human innovation, right? People are often start with simple things, and they just grow from it. And they start to do a little bit harder things once they master at a relatively simple task. And this seems all happen by human intuition, right? Sometimes we are given calculus, but sometimes we are searching this knowledge by ourselves. We are even creating new problems and solve them, which seems boost our overall innovation process. Sounds like a scientific fiction, right? But in fact, there's already an open-ended system that is running. That is nature, right? If you view this entire nature as which is like a computer system which is running, and there's an algorithm which is called evolution, and plus this billion years of computation, it created us and every single life on Earth, and more importantly, it creates our intelligence. So far, we cannot beat our intelligence in a general sense. So here's a hypothesis that if we can have a truly open-ended AI algorithms, plus we throw in a lot of computation, will this create a huge new world for us that exposes extensive, endless creativity? And probably more interestingly, will it create human-level artificial intelligence. So open-endedness itself is actually an area which starts from biology and grows into computer science. And you can go to this website and read more paper about it. But we do have some reasons why we want to study open-ended RL at Uber. Right back in 2016, David Siller, which is from DeepMind, he's one of the main author of AlphaGo. In one of his presentations, he says, AI is equal to RL plus the deep learning, right? But that seems not complete to me. Looks like RL and deep learning are methodologies to solve problems. But you still have to give the machine a problem to solve. And you're going to run out of challenges, right? It solves AlphaGo, it solves ImageNet, and you have to hand by hand inventing some task for them. What you get is an AI algorithm that solves that task. But how could you imagine a general artificial intelligence could grow out of that? It has to be involved in some kind of open-endedness process where interesting, diverse challenges are emerging out of the process. And the agent may be driven by RL algorithm or deep learning algorithm, solving them, getting better, and ready for the next challenge. And of course, there's a practical reasons that we have to, also there are more practical reasons why to study open-endedness RL, right? We are trying to see if the creativity of open-endedness could help us solving practical problems. So for example, can we create a problem and solution at the same time with increasing diversity and complexity? For example, we could identify some corner cases for safety applications. And also, as you can see later, this open-ended type of algorithm often creates its own curricular. So if you have a very challenging problem, you probably don't have to manually create a curricular by yourself. You just let the algorithm invent the curricular automatically and reach where you want. We hope we can cover this later in this talk. But I want to say that we have published this work called POET. It's our first version open-ended RL algorithm back in January. And it has been it seems to attract some kind of interest from science, a science reporter. And also we have spoken at other conferences and venues like about this. And people think it's kind of new and interesting. All right, so what is a POET, right? POET is called Paired Open-Ended Trailblazer. In the next few slides, I will summarize them, and hopefully, if you read onto those details, talk to me after the talk. But basically, we have problems and solutions, right? We always pair them. Every challenge, every problem in the system have a solution, attempt a solution. We try to solve it. So we start with something really, really simple, a simple problem with a solution which we hopefully can find it, right? And then it's all about we create new problems. We evolve these problems to generate new problems that are diverse and complicated. And meantime, every problem has a paired solution, attempted solution. So we are trying to optimize this agent or solution, right, to solve that task. And we hope we create an ecosystem where new challenges get invented and solved, which bumps up the level of capability of agent. Then this agent will basically guide the next round of new challenge task that is still within their reach, but a little bit stretch for them. So we hope to create this ecosystem where we gradually have more and more interesting things. And finally, in order to achieve that, we find out that we need to create, preserve, and utilize stepping stones. Remember stepping stone, right? Jupiter comes from something that totally don't like Jupiter. Those are called stepping stones. So we found that having them and utilize them are really important. So let's put POET in action, so you will better understand what the algorithm is actually going. Here I want to introduce Bob. We call him Bob, literally. Bob is a 2-foot simulated robot in his universe, right? And his goal is to navigate from left to right. And he has like a score scoring system which encourage him to do it. And you can put whatever off the shelf algorithm to solve this, to solve some simple ones. So yes, it started with a very easy environment. Bob on the flat ground. Bob learns to walk on the flat ground. This is our starting point. And then, how we do that? We pick some of the challenges or problems or domains that are kind of being solved, but not fully solved. And we let them mutate into new challenges, into a group of new challenge candidates or new problem candidates. And then we filtered out those ones that are obviously too difficult or too easy for the current group of agents, right? And we rank these new challenges by something called novelty. It will take two more slides talking about the mathematical definition of novelty. But you can think about it like this: like if a challenge or a problem is novel, it means it's quite different from the existing challenges. Or if I have a distance metric, this guy seems quite away in the distance metric, quite far away from the existing challenges. So we call them a novel task, right? So we filtered by difficulty level and rank by novelty. And we have this re-ranked, filtered list of candidates, new environment. And we pick one of those. Pick the most novel one that satisfies the difficulty criterion and add into the system. That's simple. By doing so, we see Bob has emerged. There are a lot of parallel universe created by Bob, by this system. And each of those has a Bob. And Bob learns to walk and navigate in this relatively easy challenge. He learns to jump over stumps. He learns to walk more or less like a human and go over all these challenges. Those are relatively easy. Also stepping stones, right? Remember stepping stones, right? We're talking about Jupiter come from something that has nothing to do with Jupiter, right? So here we are also trying to find the stepping stones. How we are doing that? Because we are starting from one and we grow into a group of tasks. So at any given time, we have a group of tasks which has each of them has an agent paired with it and try to solve with it, okay? And then every once in a while, we took some of the agent, some of the solution, and tried in other places, right? And if they doing good, okay, in other problems, it will knock out the current paired agent of that particular problem. And then this new guy will while it is still, the one copy of it is still solving the old problem, a new copy of it, a clone of it, will be solving the new problem. So for example, let's see how this transfer actually works and help the system, right? So we have seen Bob in this flat ground, and Bob is moving. And it seems making pretty good progress and have a score that is around 300, which are pretty good. But Bob seems walking in a less efficient kind of gait, right? He put his knee on the ground, which has a lot of friction, so he cannot move really fast. Then, starting from that flat ground, we created this new environment, a child environment, which has a little bit bump. But now the Bob strategy the clones, they will clone Bob and put into it. And now this new Bob cannot solving this new problem using his own strategy, right? So he gets like less perfect ground score. And then he learns from it. Because there's a bump in the ground, he has to stand up. He has to stand up. And somehow he learns to stand up, okay? And because of this transfer and stepping stones, we occasionally check if this new Bob helps old Bob in the old environment. And it actually did, okay? So this new Bob replaced its parent, right? And get back to the flat ground. And you actually get a little bit better score. This is actually more revolution, okay, because the new Bob back into the background actually gets optimized towards that environment. And it actually learns a very efficient way of evolve. And before we see that new Bob, we can't even know, okay, oh, there's actually around 350 score we can actually achieve. But this actually is achieved, right? By this trafficking. So you may ask, okay, maybe the old Bob in the old environment will eventually learn, right? It will eventually learn to stand up. It's not. We have watching this poor Bob in this environment for a long time. It improved the score a little bit, but he never gets his motivation to stand up until it gets replaced by one of his clones, learn the new skills in other environment and transfer back. And this happens a lot. So go to read our blog post. We have a lot of more kind of theoretical story talking behind it. But this is more like an illustration of ideas. Okay, so by doing this Bob creating parallel universe, put new Bobs there. New Bobs sometimes comes back to visit and knock you out of your home. We start to see this environment solution start to increase some complexity, right? So now we see some very rough space, high stump, large gap. So you definitely want to ask, can this environment be simply solved by directed optimization? So you pick this challenge environment. Let's put RL into it. Can it be solved? They can't. Because the reason is there's no curricular, right? The Bob actually stuck in a local minimum. It learns to don't go over the first large gap. Don't go try to even jump over that stump, right? He learns to try not to move, because if he falls down, he gets a bigger negative score. So a safe way of playing this game is basically stop at the first challenge, because you don't have a curricular for them, right? But Poet have a curricular, because as you constantly try Bob back to some of the environments and into new environments, right? This same Bob will experience all kinds of different environments, and it will again learn knowledge in all these environments. And all of a sudden, it will learn to hopefully solving new challenges. For example, if Bob learns to jump at over a large gap, that jump capability will help that Bob jump over a stump, right? He learns to jump in this scenario. So, and of course, if you are manually creating curricular, you probably will be able to solve some of the challenges. But in the paper, we actually do a more thorough comparison. We found out that by manually create some curricular, for example, you manually increase the stump height, right? That will get you to a certain point. After that, you're done. But Poet can still go. All right, so we see diversity and complexity keep increasing. So now Bob can navigate through all kinds of challenges, right? And he seems doing well. And quickly max out this game because of physics. It's because we are running a physics simulator behind it, right? And they can only jump that high. So right, you cannot put a mountain before Bob because he cannot just jump over it. So we also have a movie, okay, only 2 minutes, but you can watch it for free from our website. Okay, so one last thing about Bob is like I see Bob like doing this. Okay, I want to say that this is not a machine learning policy that is letting Bob falling down, because a reasonable machine learning policy will learn to stand in front of the stairs, right? Instead of just jumping over it. I created this just to show that this challenge is very hard. But will Poet create agent solve it? Yes, it is, right? He learns to kind of fly down, because not only we are measuring how fast he's traveling along that x direction, we also wanted to maximize or minimize his energy use. So this Bob learns to utilize, like he can fly down, keep balance in the air, and then kind of reach down with a minimum. So you get like a pretty good score. I call it downstairs heroes. Okay, so finally, we are thinking that an open-ended algorithm could help unlock the endless creativity of machine learning and AI. So Poet is simply a small step towards that direction. Okay, so we want this algorithm to create problems and solutions at the same time, and we are generally increase in a more intelligent way of the diversity and challenging and the complexity of those problems. And finally, we hope that these algorithms will discover capability and that the normal algorithm cannot learn in other ways. And as you can imagine, I am in parallelly having all these problems and try to find the solutions, right? So it tends to use a lot of computation. So we keep our data center very busy. Some of our colleagues are not happy. But this is probably one of the advantages you do machine learning AI research in a bigger company, right? Because you get access to a lot of computational resources. But we think that in future, we could develop algorithms that are kind of better utilize computational resources while still achieve a good kind of diversity and challenge level. Because our nature never used up all the energy come from sun to create us, right? We still got a lot of leftover so we can live and survive today. So there's definitely a way of creating more efficient, energy efficient system. So finally, what is the next step? Right, so we talk about Bob in 2D. That seems easy, but it's actually not easy. So now we need to create something in 3D, right? This is 3D Bob, right? In his known universe. Now, if you have a wall in front of Bob, right? Bob could climb over it or kind of go around it, right? Some Bob seems already learned that. We will probably release a new round of results very soon. Also, the right one is actually from OpenAI. We have a bunch of friends over there. They get very excited about open-endedness. So they created this multi-agent player system. So you have multiple Bobs inside that park. And that park could start from a fairground and getting very complicated, have waters, have bridges, have bushes, and the Bobs can interact with each other. So now you one Bob could bump into another Bob and knock down that Bob, right? So this becomes really interesting. And they already created it and released this. And of course, practical thing, right? So if we have a simulator in this scenario, we could start to imagine, right? Can we grow an environment? Can we cover some corner cases that people cannot think of? And then improve the safety of the simulated self-driving environment. And then we can consider how to generalize from simulated environment to the real life situation. Even further is, if you look at all my algorithms, they are heavily using simulators. That's actually a big obstacle to kind of prevent RL to apply in a real kind of complicated world. It relies on a simulator oftentimes. It uses a lot of data. But many of the Uber's dynamic systems, they don't have simulators, right? We could spend the whole night talking about real life RL without a simulator. But we have to talk that in future. But if you have some ideas, you can come and talk to me. And I will be super excited to share with some of our things. Okay, so I shared a lot of things about Bob and his parallel universe. I have been watching him for quite a while, last year, and he seems making some good progress. So we released the code. Please download. Please try to break it and see how things are going. If things works well on your side as well. So thank you so much. My name is Ray from Uber, and it's a pleasure to talk with you.
Thanks, Ray. Actually, we have a few minutes for the questions. If you guys have any questions, we can.
Oh, his question is, oh, you want to repeat that? Okay.
Asking for one of those experiments, how many GPUs did you need, and how much was the training time for one of the task, maybe incremental task?
Okay, for the you can refer to our paper for the details. But for the example I show you, I used about 512 CPUs, and because the neural network is relatively small, we don't utilize GPU, right? It's about 512 CPUs, yes. And because our simulator runs on CPU, right? So that's why we heavily kind of use CPU in the RL access. Go ahead, please. Oh, I'm sorry. I'm sorry.
Okay, first of all, thanks for your story about Bob. Yeah, and I have another question is, can you give us another example to differentiate what's the difference between a new environment versus like just a new task for your old training model?
Oh,
yeah.
Okay.
Can you give us a new
so
example?
Task here I saw a lot of new words to you, like task, right? Problems, challenges, environment. They all mean the same thing. They all mean the same thing. It's like if you want to apply RL to some problem or challenge, or let the agent solve an environment, they all mean the same thing. It's the target the agent try to solve. Okay? Did I answer your question? No? Okay, yeah. Let me clarify that. Her question is, I mentioned max out, right? You're talking about open-ended. It should go on forever, right? Why you max out? The max out is, in this experiment, we have a fixed torque on Bob's leg, right? So Bob cannot jump infinitely high. And because of the physical limit, we find out that this algorithm maxed out that physical limit. But let's say if Bob is also involved its torque, like max torque he can apply on his leg, we reasonably believe that Bob could do like even more challenging things. The environment could become more interesting. Yes.
A great talk. Thanks for sharing. It's very exciting. So my question is, in order to apply this like open-ended AI to other domains, what's the limiting factors? Is that because the computing resource or some other things?
I think there are several kind of limiting factor. The first thing is a simulator, right? As I said, all these algorithms abuse simulator a lot. And for Poet, we even kind of hack into the simulator and let it grow something that is really interesting. But in the real world or other scenario, you might not have access to the simulator. So how to apply open-endedness in a real life, no simulator case is still an open question, right? But people, it seems nature are doing that, right? So yes. Mm-hmm. Oh, okay. Yes. So I think the simulator thing is probably unique for RL, right? So simulator is like a simulated world, right? So RL is about an agent exploring a world, take some action when he sees something, and then get a reward. So what the agent sees or feels come from the world or simulator, and he took action, and what's the reward comes from the simulator as well.
Okay, during a time, let's have the last question. Okay.
I have a question, like how complex curriculum did you go with? Like, do you have at some point that your Bob kind of forgetting stuff that he learns in the beginning if you go like really complex? Because I mean, autonomous driving at some point would have like really complex challenges, right? And you might forget some things from before, right?
Totally. So I haven't mentioned that. You actually talking about how general this Bob can be, right? So in our new version paper, we are exploring how general these capabilities are. In the first version, we are not looking into that. So we only measure how each Bob is good at its own universe. We don't measure this Bob is that good at all the universe or part of the parallel universe group, right? So that is something that we are looking to. And we have some idea, like we probably will need constantly not only like let this Bob overfit to its own environment, we probably have to test this Bob in a bunch of other environments which are closer to each other so that we can create some kind of a partial generalist out of the system. So that is like a next step for us. Yes.
Okay, great. Well, thanks a lot for the talk.